Okay, so basically looking at question 7, we have two strictly ascending Fibonacci sequences essentially. Yeah.
Yeah.
And none of them can be um like the tail of one of the sequences can't be this basically um the other sequence. So like well, there has to have one term that's not in the other sequence. Each of them do. And my question to you is, can you see an obvious way to get there to be two common terms between the sequences? Okay, so basically the idea is like when you do the Fibonacci sequence, you have control of the first two terms, right?
Yeah.
You can make the first two terms whatever you want, right?
Yeah.
So what you can do is you can just take any Fibonacci sequence, right?
Yeah.
And then make the other ones start with two of the terms from the first one. Does that make sense?
Yeah, then you got the exact same ones, won't you? For all of them?
No, you have like so you have like one of the sequence. So just take any sequence, yeah.
Yeah.
Like 1, 2, and it's like 3, 5, 8, right?
Yeah.
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 And then the second one you can do like 1 and like 13.
Oh, yeah.
So they don't have to be next to each other. You can just take two like whatever, however far apart you want.
Mm.
Does that make sense?
Yeah.
Because you're kind of free to choose these two. Hmm. Let me ask you something. Are you allowed to do this? Are you allowed to go? Are you allowed to do like 3, 1, 4, 5? Are you allowed to do that?
I think so.
Huh?
Oh, no, it's strictly ascending.
Yeah, so it's strictly ascending. So you're not allowed to have this, okay?
Mm.
So the question is, so one of the interesting questions is if you have this 1 and 13 in common, like, do you know if there's going to be more in common or there's that's it? Yeah?
Mm.
Can you ever get more in common? Okay, so I guess that's like another part of the problem. Okay.
Okay. Possible.
Okay, so you got like 1, 2, 3, 5, 8, 13, 21, 34, 55, 89.
144.
Okay, and then you want to maybe start with here 1 and 13, right?
144, I think. Right? The last one.
Yeah.
113, 14, 27, 41,
Mm-hmm.
41.
41.
Yeah. 68, 109, 177, 286,
Mm-hmm.
and 463.
Okay, so why might not they have another term in common?
So they're getting exponentially further away after.
Okay. Um. So. Okay. So what you could maybe do is. So at this point, it has the same two things as this point, right?
Yeah.
Okay. And then we're wondering if it ever repeats again, yeah?
Mm.
So, for example, how can we say, like we said 14, yeah?
Yeah.
How can we say 14 will never be repeated in the other sequence?
Because 13 is in that sequence, but the number before it is 8, so it's gonna be higher than 14.
Yeah, like 21 is the next term and everything's bigger, so it's meant to go here, but it can't, right?
Yeah.
Okay, well that's good. How do we know like 21 is not in this sequence?
It's, it's not it's not before 27 and it's not after 14.
So it's meant to go here, right?
Yeah.
Okay, and it doesn't, so it's not in the sequence, right?
Yeah.
If we look at 27, how do we know it's not going to be in the other sequence?
Because it's higher than 21 and less than 34, but there's nothing in between those two.
Yeah, so it's supposed to go in here, but it can't, right?
Yeah.
Okay, now we take 34. Why is it not in the other sequence?
It's supposed to go between 27 and 41, but it isn't there.
You know?
Mm.
Not 41.
41 supposed to be going between 34 and 55, which not there.
Okay, 55.
Supposed to go between 41 and 68.
Mm-hmm. 68.
68 supposed to go between 55 and 89, but it's not there.
Yep. 89.
89 supposed to go between 68 and 109, but nothing.
109.
109.
Hmm. Where's
Huh?
100? Can 109 be in the other sequence?
109 has to be going between a hundred is between 89 and 144, but they're
Okay, what about 144?
144 would have gone into between 109 and 177, but something.
Okay. And what about 177?
It would go in between 144 and 233, so
Yep.
that's not there.
Well, do you see a pattern?
It's like not going in between the next in between, I guess.
Yeah, so do you think you can state this pattern in notation? Can you state what this pattern is?
Okay, maybe yeah.
Okay, give me a statement for this pattern. You see what there's a very definite pattern, right?
Yeah.
Okay. So I want some notation for this. So let's I won't tell you anything, but I'll give you a second. And if you have no idea, I'll give you some starting notation, okay? Okay, so you have the right idea. Let me turn this into proper notation, okay? So you can have a sequence, like this sequence can be called sequence A, right?
Yep.
And this one can be called sequence B. Does that make sense?
Okay.
And then what you could say is instead of labeling it A1, A2, A3, is because notice how we started at 13, right?
Yeah.
We can call this um we can call this A2, yeah?
But isn't that A2 for like the other sequence?
This one's B2.
Oh yeah.
Does that make sense?
So A. Uh. Oh yeah, because it looks a bit confusing. Because normally two would be A2.
Yeah,
But
so the point is, this is actually A6 or something, but we kind of forget about it because it doesn't repeat anyway, right?
yeah,
And then we just call it A2, you know?
yeah.
And then, so the whole point of calling it A2 and B2 instead of A1 and B1, right,
Mm.
is so that we can have a term A1 and B1 in front of it, and that'll give us the definition of the next terms, right?
Mm.
And then once we got that, we have all the terms, yeah?
Yeah.
Okay, so the A1 and the A2 and the B2 are the ones where they're equal, right?
Mm.
Um, so we can say that this is like, for example, the second time they're equal, yeah?
Yeah.
Because the first time they're equal could be at the very start, yeah?
Yeah.
But the second time they're equal guarantees there's at least a term before that, yeah?
Yeah.
Does that make sense?
Yeah.
Okay, and then the thing we had with 14, that's B3, right?
Mm.
So we want B3 to be bigger than A2 but less than A3, right?
Yeah, and that's two.
Yeah, and then for the A3, so A3 is the 21, right? And we want that to be bigger than the B3. Yeah?
But less than B.
Less than B4, yeah.
Mm.
So it kind of goes like this, right? And then the B4 is bigger than the A3, but it's less than the A4, right?
Yeah.
And then this kind of just keeps going,
Yeah.
you see? Yeah.
Mm.
So what we want to show is we want to show that BI is less than AI. Yeah. Um, and then we also want to show that AI is less than BI plus 1, right?
Yeah.
For all I greater than or equal to what? For all I greater than or equal to 2. Yeah? Maybe not quite. So this is for all I greater than or equal to 2. Yeah? But this one is for all I greater than or equal to 3. Yeah? Does that make sense?
Yeah.
So if you have that, um, that'll prove that the sequences never meet up again, right? Does that make sense?
Yeah.
So here, I guess you start with the assumption. I guess here is this is A1, right? This is B1. The A1 is bigger than the B1.
Mm.
So we have A1 is bigger than B1 is the starting point, and then A2 is equal to B2. Yeah?
Yeah.
Does that make sense?
Yeah.
Okay, so we have a statement now, right?
Huh?
And we have a statement. Yeah?
Yeah.
And if this statement is true, then the problem is solved, right?
Yeah.
So it just suffices to prove this statement, yeah?
Yeah.
Okay, so maybe have a think about how you might prove that, and then we'll discuss, yeah?
Okay.
Okay, so I think this is essentially like the way you kind of naturally do it is what might be called an induction, mathematical induction, okay? So you remember like the thing about proving stuff is you need the definitions, okay? So here we can log that a1. So a1 is bigger than we got this to start with, yeah? And we can assume that because one of them has to be bigger. If they're equal, then the terms of the sequences are basically the same from then on, right? Hello? Are you there?
Oh yeah, sorry. I didn't.
Okay, so you can assume a1 is bigger than b1, but the thing is, a3, so how do you get a3? How do you get b3? Well, we use the definition of the sequence, right? So, for example, you have that a3 equals a2 plus a1, right? And that's bigger than b2 plus b1, right? So a3 is bigger than b3, yeah? So we have the I equals 3 case here, you know? Does that make sense? And we also have b3 equals b2 plus b1, right? But b2 is just the same as a2. So therefore b3 is bigger than a2, yeah? You see? So it's true at the start, and we kind of want to show that if it's always true up to a certain point, okay, then the next one is true. Okay. Does that make sense?
Yeah, that makes sense.
Yeah, so at the moment we got this part here.
Yeah.
It's like true, yeah?
Okay.
Okay. So think about how we prove the next part's true, how we prove A3 is less than B4. Well,
Not yet.
what?
Sorry.
Yeah, so A3 is bigger than like less than B4. Let's see if we can prove that, okay? So here we have B4. And we also want to prove that A4 is bigger than B4, yeah? So B4 equals B3 plus B2, right?
Yeah.
But we have that this is greater than, so B3 is greater than A2, right?
Yeah.
So the B3 is greater than A2, and okay, we don't have anything for B2 right there. This is the same as A2. Then A4. Okay. A4 equals A3 plus A2. Okay, so we have, how can we compare A4 and B4? So we have B3 is greater than A2. And we have B2 is equal to A2, you know? So B2 equals A2, and then B3 is less than A3, right? So these are equal. And the B3 is less than the A3. So A4 is bigger than B4, right?
Yeah.
Okay. Now what about um A3 and B4? Okay. So A3 is A2 plus A1, right?
Yeah.
Okay, so B4 is B3 plus B2. So the B3 is already bigger than the A2, right?
Mm.
And the B2 is equal to the A2, which is also bigger than A1, right?
Yeah.
Yeah, so we have this as well, yeah? That's all true, yeah?
Yeah.
Yeah, so basically we want to keep continuing showing it's true, so we can assume it's true, so this is how induction works. We can assume it's true up to the point, well, let me just, it's A2, B3, yeah? A2, B3, A3. There's A2, B3, A3, B4, A4, so on, right? Like we can assume it's true up to like, for example, AI, right? Where I is greater than or equal to 4, because we've already shown it's true up to 4, yeah? Okay, and what we want to do, so at the very end it's like BI is less than AI, and it's AI minus 1, okay? So that's what we have, and we want to prove that this is less than BI plus 1, right?
Yeah.
Okay. And we also want to prove if we have something like this, or just up to the BI part, or up to the BI plus 1, that it's also less than AI plus 1, yeah? And that'll restore the assumption, so then we can just keep doing that. Does that make sense? Okay, so how do we prove that? Well, we just need to think back to what we did, okay? So BI plus 1 is equal to BI plus BI minus 1, right? And AI plus 1 is equal to AI plus AI minus 1, yeah?
Mm.
And what do we know about AI and BI? So we know that BI is less than AI, yeah?
Yeah.
And we also know bi minus 1 is less than ai minus 1, yeah?
Yeah.
So that means then we know that bi plus 1 is less than ai plus 1, yeah?
Yeah.
So we can actually do that induction totally separately. Okay.
Yeah.
Okay, now why is like ai less than bi plus 1, yeah? So this is bi plus 1 here. And then ai is ai minus 1
Mm.
plus ai minus 2, right?
Yeah.
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 Okay, but we know ai minus 1 is also less than bi, right?
Mm.
Yeah?
Yeah.
Because that's what's been happening. That's this, yeah?
Yeah.
And we also know ai minus 2 um that's this bit here is less than bi minus 1, right?
Yeah.
And these plus together is just equal to bi plus 1, right?
Yeah.
You see?
Oh, okay.
So then we proved that if we have it up to here, it'll just keep going, yeah?
Yeah.
Okay, and this means it'll just keep being true forever, okay?
Yeah.
Okay, so do you see how that solves the problem? I'll give you a little bit to consolidate.
Yeah, I see how.
You see how it solves the problem?
Yeah, because if it this works, we're trying to prove that it works for every like every number in the sequence, and it just proves it. So that means it works.
Yeah, so it proves that like if they're ever equal, right?
It
And
can't be equal again.
it can't be equal again, right?
That's two.
But it's not quite that, okay? So the thing that we actually needed was that we needed a term in before that, right?
Yeah.
So it has to be equal, and then the term before is not equal, right?
Yeah.
So if it's equal and the term before is not equal, then it can never be equal again, right?
Yeah.
Which gives you room for. So that's not the same as saying they can only be equal once, because they could be equal and there's no term before, right?
Yeah.
So um, so that's why like the 1 and the 1 were the first terms, yeah.
Yeah.
Okay, so you just gotta be careful to take care of those cases. Like if you have two sequences and one term is equal, okay, the second time they're equal, the term before, yeah, can't be the same, right? And then it can't be equal again, yeah.
Yeah.
Okay, but that doesn't mean it can't be equal for the first time, okay. And we know it can be equal for the second time just because we have an example, right? Yeah.
Yeah.
But this proves it can't be equal again for the third time, you see? Does that make sense?
That makes sense.
Yeah, so this is a really nice problem. Like, it's actually, the last question in junior A level was meant to be like one of the hardest problems in the world, but I guess this time it wasn't too bad. It's just more of a proof writing experience. So, yeah, no, I liked your willingness to try it. This was meant to be a very tough problem. No one, well, maybe one person solved it in the exam.
Mm.
Um, yeah, so that's
Yeah.
pretty cool, right?
Mm.
Yeah, so it's really like the pattern is there, and you have to kind of figure out a way to write it down in notation. You know?
Mm.
Yeah, so it's pretty crazy you're trying this. This is Yeah, this is definitely difficult for like even year 10 students. So, yeah. Do you have any more questions?
Not really.